those whom I met, long ago, now I'm not able, those whom I met in the early 80s, in Jadwizin, for instance, for open days in model theory and set theory, Hard Times for Poland, September 1981. And then in Freiburg, June 81, Gurewicz. And then Fokion and Vananen again, and Kaufmann and Gurewicz and Schmerl in 82 in Stanford, where we were preparing a big book on model theoretic logics. And then in 85, my first visit to Campinas, where I met so many nice people, including Javier, whose talk I listened with great admiration today. And then 2 months ago, I met the new sort of new generation. I don't know. Can you see my talk? Can you see me?
Yes, we can see your talk.
Can you see? Okay, these are the people.
Daniele, we can see your talk, no problem. I just closed your camera because there were, again, some audio problems, but I think it was going to be okay like this, please.
Okay, the network is very poor in this mountain village. We protested, but we couldn't repair the problem. So 2 months ago, the young generation, Aliano, Nogueira, Chris, Metcalf, Amanda, Cintula, Flaminio, greetings to everybody, all those who I never met. So my talk is, first of all, let me paraphrase. The goal of this event is together to discuss problems in their respective areas and potential points of interaction. And the two areas are model theory, especially finite model theory, and many-valued logic. Can you listen to me now? Well, or?
Yes, it's going well.
Okay. Of course, having to talk about model theory and many-valued logic is, in my opinion, or at least for me, very difficult because, yes, 50 years ago, I worked in model theory, and today I'm working in many-valued logic. And in particular, I have to apologize to both model theorists and many-valued logicians, because many-valued logicians will think that the things I say are well known, so I shouldn't tell them. And model theorists would do the same for model theory. In particular, I apologize for the intersection of these two sets, who will find all of my talk completely trivial. So double apologies to intersection, apologies to model theory, so what trivialities I will say, model theoretical trivialities, and symmetrically to many valid logicians. Double or triple apologies. I would like to start with a presentation of the oldest logics, the two oldest logic, because the presentation, which is from the viewpoint of 2020, so it's 2 years ago presentation, is surprising because it shows the tremendous amount of analogy between the oldest logic and another logic. The oldest logic is specified by the two-element set with the natural order 0 smaller 1, the discrete topology, we know, the natural and at the moment, having the property that x arrow y equal 1, if and only if uniquely specifies the arrow, because then x arrow y equals 0 if and only if x equal 1 and y equals 0. So you see. Well, the referee asked me, the referee of this paper, asked me not to write with the infix notation, but you will be so tolerant that you will access of this arrow map. It follows that x arrow, y arrow z is equal to y arrow x arrow z. It is the sort of exchange of premises. Let's call it the exchange property, telling us that the order of premises is irrelevant in this logic. The premises form a set, and order and repetitions are useless. Well, this logic, once you define negation by x arrow 0, 1 as negation 0, and disjunction as not x arrow y, is Boolean logic. Although, and I want to stress this, Boole didn't have a total operation for disjunction. But because he was considering logic and probability together, he only had disjunction for incompatible events. His disjunction was a partial operation. The algebras, and here comes algebra. If you take equivalent formulas, you get Boolean algebras. Logical equivalence immediately factors the absolutely free algebra of functions into an algebra, and the algebras you get are Boolean algebras. And they are defined by the following equations. There are 6 equations, which is a very useful axiomatization by equations of Boolean logic and algebra: associativity, neutral element, double negation, saturation with top element, and then this strange axiom, which has a deep meaning, and finally, x or x equal x, idempotency. Now, the second oldest example, it is here. Instead of the 2 elements set 0, 1, we have now the unit real interval with its, and now a continuous function, let's say map, such that x map 1 max y equal 1 if and only if x smaller equal y. And let's assume what for Boolean logic was given for free, because the arrow defined uniquely the implication. So let's assume exchange of premises is precisely as in Boolean logic. Then, with the same definition of negation and disjunction, we have Łukasiewicz logic, Łukasiewicz infinite valued logic, the second oldest example. The algebras of logically equivalent formulas are C.C. Chang MV algebras, and they are defined by the following 5 equations. Before we had 6 equations, now idempotency is no longer true. Repetita juvant. And this was found in the Journal of Symbolic Logic 2 years ago. And it is interesting because you see, the analogy is so deep, there must be something more than, let's say, a random fact here. I want to talk to you about the analogies. First, I give you examples that were already mentioned in the beautiful talk by Javier, by Godot, and implicitly by Chris. The unit real interval equipped with negation, 1 minus x, and truncated addition, the minimum between 1 and x plus y. This is the standard MV algebra already encountered in this talk, in other talks before mine. More generally, the unit interval of any lattice order of an element u bigger than 0, and you consider that unit interval. any algebra of 0, 1 valued function over some non-empty set X, with the operations induced by the standard MV algebra. This is the most general semi-simple MV algebra, intersection of maximal ideals equals 0. A Boolean algebra is just an MV algebra where X or X equal X, where idempotency, the good old idempotency, comes back. But MV algebras are immensely richer than Boolean algebras. First of all, let's characterize Łukasiewicz implication additionally to what I proved in the analogy between Boole and Łukasiewicz. If you have a map which is continuous and has the order property and the exchange property, and if you set negation and addition, you obtain with this map is uniquely isomorphic to the standard MV algebra. So you immediately get the standard MV algebra, which we already know, by a minimalist implication. It must be continuous. It must have the order property, respect the order of the unit interval. And it must have the exchange property for premises. X implies Y implies Z, equal Y implies X implies Z. And in particular, you get the Smed-Magret theorem stating that there is only one possibility up to continuous, order-preserving, monotonic isomorphism, namely Łukasiewicz implication. When you have such extremely powerful and impressive characterization theorem, you must conclude that there is at least something in Łukasiewicz logic as there is something in Boolean logic. Look here, the two axiomatizations. By the way, we are able to axiomatize Łukasiewicz by 5 equations because of Kolarczyk result that dropped the commutativity axiom. It is not necessary for Boolean algebra. It's not necessary for MV algebras. Boolean logic stands to the two-element set, as Łukasiewicz logic stands to the unit interval. Boolean logic stands to Boolean algebras, as Łukasiewicz logic, L' stands to MV algebras. Background reference. Then first, in fact, it was chronologically the second, but it's the first basic theorem in Łukasiewicz logic is the completeness theorem that Chang proved in Transactions of the American Mathematical Society in 1959. An equation holds in all MV algebras if and only if it holds in the standard MV algebra. So what the two-element set does for Boolean algebra, an equation holds in all Boolean algebra if it holds in the two-element set, the same Chang's theorem does for MV algebras. And then an immediate corollary following from Birkhoff's analysis of equational logic. We have immediately a visualization of the free MV algebra over n generators. Well, it is what you can get from the coordinate function, also known as projection or identities. The xi giving the coordinate of a point in the n cube by pointwise applications of the operations of the, just as for Boolean algebras, the n to the n. Okay, here it is what you get from the identity functions by applying truncated addition and negation pointwise. Characterize these functions. I will proceed by a necessary and then a sufficient condition. What are the properties of the coordinate functions that are preserved by truncated addition and the operation 1 minus x? Well, the first is continuity. The second is that you get finitely many linear pieces. And the third is that coefficients of each piece are integers. So integral, piecewise linearity, and of course, continuity. Therefore, these conditions are necessary for a function to belong to the free and generator MV algebra. So Chang could have added a corollary. Necessary condition in the free MV algebra are these three. Are these conditions sufficient? For instance, this is clearly a piecewise linear function with integer coefficient. Can it be coded by a formula? Does it belong to the free MV algebra? Does there exist a formula in Łukasiewicz logic? And here I will, in a sort, paraphrase Godot, as Luis who said this is a qualitative. It's also quantitative because we can express exactly what Pavelka logic does, and we are very powerful logic. And the answer is yes. This is a theorem of 8 years before Chang's completeness theorem. The free and generator MV algebra is given by all continuous, piecewise linear functions, each piece having integer coefficients. These are known as Macnaughton functions. So this is the other half of Chang's completeness theorem, giving only necessary condition for which functions are coded by Łukasiewicz formulas. Any free MV algebra over many generators is a limit of free finitely generated MV. And variable formulas codes the Macnaughton function. The variable codes the identity function, truncated addition codes the truncated sum, and not phi codes 1 minus f of phi. It's extremely simple. It is geometric. It is analytic because we have piecewise linearity, which means differentiability in any direction. And we conclude that L dash formulas code precisely Macnaughton functions. Examples that I will use in the second part of my talk, because I want to go to first order Łukasiewicz logic, are these problem is integer coefficients. But you see the formulas give you the integer coefficients. These sigmoidal functions arising from 2 minus nx certainly have integer coefficients, are piecewise linear when you cut them up to 0 below 1, and are so definable for formulas. Observe that these are Macnaughton functions. You can express them in Łukasiewicz logic. In particular, and here I would like to draw Luis' attention, for every rational in 0, 1, there is a one variable formula, mu bigger equal r, whose Macnaughton function states, I want truth values equal to 1 starting from r. So we have threshold functions even if we don't have rational numbers. What is the advantage of these threshold functions saying my truth value is bigger equal than r, my truth value is smaller equal than r for any rational number? It is that the logic will not add numbers in the language, and hence, due to its magic properties, it will be NP complete. But let's go on methodically, because these considerations will be applied soon for first order Łukasiewicz logic. In fact, this is the starting point of our analysis of the finite model properties of Łukasiewicz logic. They are based on Chang completeness, which gives the first half of McNaughton representation of NV algebras, not only the free ones, but also any NV algebra, which is a quotient of a free one. So it is a localization of the free algebra. If a free algebra is McNaughton function on an n cube, a quotient is in general, and we will see there are subtleties here, restrictions of this function to a closed set. Everything is compact, everything is piecewise linear, everything's continuous. Understanding the notion of finite model in the propositional case will be decisive for understanding finite model in the first order case, finiteness. What is a finite model, I ask? Oh, my connection is unstable. I'm sorry. I try to do my best. What is a finite model in Boolean propositional logic? Thank you, Carles. In Siena is much better than here. What is a finite model in Boolean propositional logic? Already this question is extremely interesting because we have 6 synonyms. That means people didn't easily understand finite models in Boolean propositional logic. Let's see the 6 synonyms. Some are clear mathematically, others are not. Finite model, finite truth valuation of a formula, so finite possible word, and this comes out, and I imagine Flaminio in a few days will mention possible words in Boolean logic and in Łukasiewicz logic. Essentially, possible word is a model. Homomorphism into 0, 1, okay. Homomorphism of algebras or homomorphism of the absolutely free algebra, okay. Evaluation, truth valuation of a Boolean function. Point in the vertices of the n cube. Having these 6 synonyms, one is computational, one is geometric, one is typically logically truth valuation, another is probabilistic, possible word, occurrence of an event, tells you, first of all, the denseness of the notion of finite model, and second, the difficulty we had to understand the 6 possible views of this notion. Observe that by saying that a model is a point in the n cube, a vertex, comes out because every truth valuation, V, is a function from the formulas into 0, 1. So it depends only on the values you give to the variable, because we are with free algebras or absolutely free algebras of formulas. And so every valuation is just a vertex of the cube. 0, 1 raised to x1, xn, in other words, 0, 1 to the n, in other words, a vertex of the n cube. And we have 6 synonyms, of course, in Łukasiewicz logic, but the adjective finite is now rational. Rational model, rational truth valuation, rational possible world interval, evaluation of a McNaughton function at a rational n cube, 0, 1 to the n. Not a vertex now, but a good, honest point in the n cube. So let's go back and forth and back and forth again to contemplate this deep analogy, this deep extension from Boolean to Łukasiewicz logic against looking at valuation or models as point in the n cube comes from the absolute freeness of the algebra of formulas, or if you prefer, from the freeness of McNaughton functions. And now comes the benefits of finite models in Łukasiewicz logic, mimicking the benefit of finite truth valuations in the satisfiability problem for Boolean algebra and logic. The first observation by induction of a length of a formula, here comes syntax, here comes the non-ambiguity of the syntax, and here comes induction, the absolute value of each coefficient of each linear P is bounded by the length of the formula. Well, this is trivial because 1 minus is just rounding up around 1/2 and doesn't change the derivative, the coefficients of a linear polynomial. And addition sums up, and the sum corresponds to the sum of the length of the formula. So you see it immediately, this. So the linear pieces of a short formula are small. Second, any n-variable formula is satisfiable if there is a small point in the unit cube such that the formula or the function gets truth value 1 or is evaluated to 1. This point is rational and the denominator is polynomially short in the length of the formula. This is another triviality by induction and by Hadamard theorem. So you see, certificates for the satisfiability of a Łukasiewicz formula are small, finite, rational in this sense, small denominator, they're after all rational pairs of integers in binary notation, points in the cube, polynomially small, and hence, for some polynomial, only depending on the dimension, you can check satisfiability in less the q of length of phi steps. In other words, certificates of satisfiability are easy. There are only few points with such small denominator in the n cube. Corollary, 1987, when I first met more or less a model theorist in 81 and 82. L satisfiability is in NP because of what we have just seen, and it is NP hard because it contains the Boolean SAT problem. Therefore, Łukasiewicz complete. Good. I don't know if adding numbers would preserve this precious property. In any case here, we don't add numbers and we have a typically quantitative logic where we can say my truth value is bigger than Q for any rational Q. And these are the three, in my opinion, building blocks of our attempts to speak of first order Łukasiewicz. There are many, many constructions in the literature. I will mainly deal with one construction. I will not give a complete bibliography because this is not the aim of my talk. The aim of my talk is to publicize Łukasiewicz infinite valued logic in all its forms, showing that it is here to stay as a deep analogy of what Boolean did for two-valued logic, a very deep analogy. Well, the first thing to insist on the importance of Łukasiewicz logic is to list a few of the many deep, beautiful, structural, mathematical properties of this logic. Here is an image that I hope you will remember. First of all, NV algebras are Łukasiewicz logic formulas up to equivalence. And Łukasiewicz logic is presentation of MV algebras for the computer. And then going counterclockwise, we have Chang's completeness theorem, stating that the standard MV algebra generates the variety of equivalence classes of formulas. We have NP complete satisfiability. We have the characterization of Łukasiewicz implication and as the only continuous 0-1 valued implication. I don't know if you can listen to me. It would be so sad to speak only to myself.
Daniele, we are listening, no problem.
Very good, I go on.
Yeah.
If at some point you don't hear anything, please tell me, because I don't like to speak to myself. I'm too young.
Don't worry about that. Don't worry about that. Yeah. I will let you know.
Again, yeah, characterization of implication as a minimalist implication having order and exchange property. A theorem which visualizes geometrically free objects, visualizes the essence of formulas, the formulas up to equivalence. As in Boolean logic, we speak of Boolean functions when we want to visualize formulas up to logical equivalence, Boolean formulas. And finally, the last three properties on the left-hand side, the easiest one is definable by these 5 equations, very simple, extremely natural. And then, as already mentioned in this session, MV algebras happen to be equivalent, categorically equivalent, so identifiable with lattice-ordered abelian groups with a strong unit, with an element whose multiples go to the end of the group. This is a categorical equivalence that will find application when we speak about soon. Finally, the maximal spectral spaces of MV algebra are precisely or compact Hausdorff spaces. A corollary of this is that when you consider MV algebras with their states, and I'm sure Flaminio and others will speak about this finitely additive probability, are the same as Kolmogorov sigma additive probability. Okay, thanks to the Krupa-Panti theorem. I want to give you a very short and perhaps I could avoid it, but let me mention it because there are applications of Łukasiewicz logic and its computational machinery to much computational functional analysis for quantum mechanical C-star algebras, but using Elliott classification that prove that a certain class of C-star algebras is classified by lattice-ordered abelian groups with unit, and using the gamma functor, you can say the following theorems. One of them, recent, 2022, will appear in 2000. No, it's already online. Countable MV algebras are in a functorial 1-1 correspondence with approximately finite dimensional C-star algebras whose Elliott classifier is lattice-ordered. These are approximately finite dimensional, means limits of finite dimensional, and I will show you the importance of this class of C-star algebras in mathematical physics. Truth values in Łukasiewicz logic, therefore, are relative dimensions of projection in AF C-star algebras. And finally, for many AF C-star algebras preeminent in the literature, the algorithmic machinery of Łukasiewicz logic, the NP-complete algorithmic machinery of Łukasiewicz logic decides in polytime if a projection is trivial, so 0 or 1, central, commutes with everything, or full, never 0 in any maximal ideal. To show you the importance of AF algebras with lattice-ordered classifier Elliott classifier, you will find on the right-hand side, functional analysts and physicists. On the left-hand side, finite MV algebras, chunk algebras, see the Freon generator, because the two things live in symbiosis. And this is the end of the first part of my talk. There are 2 parts. There are not 5 parts. And probably the second part will be a little shorter than the first part. So far, we have dealt with Łukasiewicz logic in the context of Boolean logic, showing that it stands to the unitary interval as Boolean logic stands to the 2-element set 0, 1. We now move from propositional to first-order logic with identity. Let me underline, with identity. Let me underline, with honest-to-God identity as identity. Model theory with identity. Finiteness properties of models in propositional logic, so rational models which are easy to check in the satisfiability problem, will carry over to classical and Łukasiewicz first-order logic. Here the standard references are 2. This book, published in 2011, and an article published in 2011. So this is 10 years ago. Our program is that since in classical first-order logic, L omega omega, a notation that we found in Javier's talk, by the way, a model is a non-empty set U for universe, with extra machinery for constant function and relation symbols. In classical first-order logic, M is also equipped with a natural 0-1 valued yes-no identity relation on elements of sets. This is equal to that. This element is equal to that element. Likewise, the universe of any model in L dash omega omega, the first-order Łukasiewicz logic we are going to construct, will always come equipped with constant function relation symbols and a natural 0-1 valued identity relation. How do I mean a natural 0-1? Who gives us a natural 0-1 valued identity relation? How comes? Never heard of. Natural. In the literature, we have plenty of similarity, approximate equality, but natural, what is it? Our program is in L dash omega omega, in first-order Łukasiewicz logic, the universe U is a set X of unit vectors forming angles which are acute, smaller equal pi half. In a Hilbert space, H, where you can measure angle, by the way, in fact, Hilbert space is for that, whose linear span is dense in the Hilbert space. So we have the completeness of the Hilbert space, the angles that the Hilbert space provide, so that our identity degree is the scalar product. The identity degree of any 2 elements. Now, elements which in classical model theory were points, here are much richer structure. In classical model theory, points in a set, a very poor structure after all, with respect unit vectors in a Hilbert space. Each model will be equipped with function, relations, having natural congruence, and congruence will now mean uniform continuity, properties with respect to this 0-1 valued identity. Everything shall be extremely natural. Now, definition of universe of a model. A set in a Hilbert space H is fundamental if it is dense, its linear span, in the Hilbert space. A quiver, formally, because I didn't want to write quiver in my paper and book, an MV set is a pair with a set X in a Hilbert space where X is a fundamental set, so it is dense, is a set of unit vectors forming acute angles, any two vectors between them. So it's a very natural notion. A Hilbert space, a subset whose linear span is dense, and angles between these unit vectors should be acute. The scalar product, of course, will be the identity degree of these two vectors, just as yes or no will be the identity degree of 2 points in a set. Observe here, set becomes Hilbert space. Equal or different becomes the 0, 1 valued scalar product between vectors forming unit angles, vectors which are unit vectors. So in particular, the scalar product by Schwarz, Cauchy-Schwarz, the scalar product will be in the unit interval. So the identity degree is in the unit interval. Observe that a vector is equal to another vector if its if their scalar product is equal to 1. I give now a miserable picture of MV sets. Think of a quiver, if you wish, and then make infinite, but take care that angles should always be acute. So unit arrows forming acute angles in a Hilbert space whose linear span is dense in the space. Observe that if these arrows are pairwise orthogonal, these are unit vectors which are pairwise orthogonal. What are they? They are an orthonormal basis in the Hilbert space. And we recover in classical model theory. Now a function. A function cannot be defined as a function because we must have congruence. Here is the definition of congruence. The minimum between the distance of, now suppose you have vectors v1, vn, w1, wn, and a function with n places. Then you ask that the minimum degree of identity between the vi and wi is smaller or equal than the degree of identity between fv and fw. What does it mean? For instance, if this minimum is 1, in other words, v1 is equal to w1, vn is equal to wn, then it must be smaller or equal. So in other words, f of v must be equal to f of w. This is our congruence property. And this is magic. Composition of MV functions are functions. And when x is an orthonormal basis, this inequalities boils down to the familiar congruence property of function. If v equal w, then f of v equal f of w. The proof is elementary. I will not insist, but observe that the magic congruence property 3 star has an immediate effect in proving the uniform continuity of congruence. This is a very poor image. It's very difficult to paint a function in Hilbert space between a quiver of arrows and another quiver of arrows given by a function which is uniformly continuous. A relation is the same thing. You ask the same congruence property. So when the minimum between v and w is 1, then the difference between R of V and R of W must be 0. They must have the same truth value. And again, every MV relation is uniformly continuous in the norm topology of the Hilbert space. And when X is an orthonormal basis, we recover the traditional congruence property of relations. The sketch now is a little bit brighter than for functions. You have a continuous assignment of shades of red to the unit vectors in this MV set. Now we have reflexivity because the scalar product of X with X is 1. We have symmetry because scalar product is symmetric for when it is a real number. And transitivity fails. In either form, identity degree xy and identity degree of yz smaller equal identity degree xz, or even with the weaker infimum fails. Example, take these 3 vectors and patiently verify that the identity degree infimum, the identity degree of AB infimum, identity degree of BC, which is bigger than the conjunction, is this quantity, which is bigger than 0, which is cost by half, which is the identity degree of AC. So it is bigger, but it should be smaller. It fails. So what should we do to have an honest identity measure? What is transitivity? Transitivity is provided by a fantastic notion. We approach this notion by thinking of the case when the matrix M is Boolean, so 0 or 1, yes or no, symmetric, so we have symmetry, and unit diagonal, so reflexive. Then the following conditions are equivalent. There is an equivalence relation such that M is the characteristic function of the equivalence relation, in the sense that for any ij, the entry mij is 1 if and only if I is equivalent to j. So now we are asking ourselves, in the Boolean case, what is the matrix, the characteristic function of an equivalence relation? Characteristic function in the usual sense, I am equal to, what is it? And the answer is surprising. The matrix must be positive semi-definite in the sense of the following technical but well-known and extremely familiar and extremely natural definition, which will clearly seen in 2 minutes to provide what we were looking for. Here is the definition on any non-empty set. Before it was 1, n. A function y squared to the complex number is positive semi-definite if for any n complex number gamma 1, gamma n, and elements in y to the n, we have this positivity inequality. This is not so much evident as McNaughton theorem, I admit, because so analytical, so luckily we have a characterization. Positive semi-definite, symmetric, and for every row 1, row n, some aj, raj, ri, bigger equals 0, or this matrix is the product of a transpose by a matrix, Q transpose times Q. So it's positive in all sense in quantum mechanics. So positive semi-definiteness is necessary for the gram, it's called gram matrix, with the scalar products Vi, Wj of an MV set to exist. The following fundamental result from Hilbert's theory. Problems?
Daniele, I just want to let you know that there are 10 minutes left, including
Fantastic.
discussion.
Look,
Thank you.
just, I don't know if you see, I have a watch here and I am extremely careful because, as Giancarlo Rota used to say, if in the last minute of your talk you start saying that you have a proof of Riemann hypothesis, people will get nervous and some of them will leave the room, okay?
Okay.
This is the great wisdom of Giancarlo. So positive semi-definite is necessary for transitivity. The following semi-definite is sufficient. Kolmogorov dilation theorem. The positive semi-definites of a matrix is necessary and sufficient to reconstruct a Hilbert space such that the entries of this matrix are the scalar product of a fundamental set in the Hilbert space. In other words, if you want to see the scalar products of a quiver of unit vectors in Hilbert space, look at the matrix given by taking scalar product of a vector with another vector in the quiver. This should be positive semi-definite, and vice versa. If you have positive semi-definite scalar product, in other words, if the scalar products form unit diagonal, symmetric, positive semi-definite matrix, then rest assured that they are in an MV set for some uniquely determined, that's another extra benefit of Kolmogorov, uniquely determined Hilbert space. And now comes the finite model property, because Kolmogorov dilation theorem states that positive semi-definiteness can be checked by restricting to finite dimensional submatrices. So again, what we had for the propositional case to prove its NP completeness now is the sort of finite model property of Kolmogorov dilation, an enormous matrix, check submatrices. So the creation of the quiver of the MV set of the universe of your model and a transitive, symmetric, reflexive, identitive comes by steps which are finite. This slide is a little bit boring, but it tells you that dilations and positive semi-definites are well established in the literature, mathematical and computation, and there are references here. Be patient for this. It looks that I've been looking for dilation before trying to invent transitivity. No, it would be in a quiver, in a Hilbert space. And one day, a physicist in Austria wrote to me, did you try Kolmogorov dilation? Okay, that was an illumination. Now about the expressive power of this first order Łukasiewicz logic in Hilbert space based on Kolmogorov dilation and positive semi-definiteness. First of all, quantitative, just as propositional Łukasiewicz logic is quantitative. We have threshold functions. So we can say, for a relation, for instance, my truth value is bigger than 3/4, bigger or equal. My truth value is smaller than 1/3. By assuming at outset that you have an orthonormal basis, you have first order logic. So L dash first order, then classical logic, it is strictly stronger because you can say that the identity degree between two elements is in a certain closed rational interval. Or you can say implication between such statements well beyond the expressive power of first order logic. Of course, Here we have a natural 0-1 valued identity. You can speak in the same terms for implication. So you have quasi-equational logic extending Maltsev logic for a 0-1 valued logic. So you can put the problem of quasi-equational or equational, if you wish, logic in this context. And the same for terms. You can say this relation holds for these terms, T1, Tn, with truth value in A, B. A and B rational numbers in the unit interval. So we have universal algebra plus relation, which is model theory. If you read the beginning of Chang and Kiesler, what is model theory? Universal algebra, Birkhoff, Maltsev, plus relations, plus a continuous, reflexive, transitive, symmetric, 0-1 valued identity in Hilbert space where you can measure angles. Now, to prove the compactness of this logic, I ask you to go back to your undergraduate logic years. When you prove the compactness of Boolean logic, Gödel's theorem, by the way, well, you added all the variables, and at each step you decided to add a variable or its negation according which of the two preserved finite satisfiability. In this way, you proved that finite satisfiability implies satisfiability. XB or not XB, that is the question. And you go on at the end with evaluation. Having finite satisfiability, you get step by step at the conclusion of it, satisfiability. The same holds for Łukasiewicz logic. Instead of XB or not XB, you use this threshold function and say, has the truth value to be bigger, equal, or less or equal than R for each rational. Luckily, rational numbers are countably many. At the end of this, via Kolmogorov dilation, you get finite satisfiability implies satisfiability. This is one interesting application in logic of Kolmogorov dilation theorem. So, I write Hilbert, a musician. I wanted to write Hilbert. We have Hilbert, okay, sorry. And then Herbrand, the universe, and then, sorry for these 3 errors. By Kolmogorov dilation theorem, positive semidefinites can be checked by restricting to finite dimensional submatrices. Hence, a set of formulas in L dash omega omega is satisfiable if and only if it is finite. By Tarski-Seidenberg, we conclude that checking tautologies or unsatisfiables is recursively enumerable. Here are the 5 steps leading to this first order logic based on finite models, meaning rationally easy to check, or at least we have recursive enumerability. We can expect more in a first order logic. And Łukasiewicz implication is the unique continuous zero-valued implication on the unit square. Łukasiewicz logic is here to stay. Other attempts, among many others, are listed here. And since you have my slides, you will check. Summing up, we have this point as the unit vector, equality degree scalar product, universe MV set, quiver, NRE function, uniformly continuous function, characteristic function, positive semi-definite unit diagram, M relation, Gödel compactness theorem, compactness of L dash omega omega, Herbrand theorem, Kolmogorov dilation, refutation algorithm, Tarski-Seidenberg. The set of tautology is recursively enumerable. The set of L dash tautology is recursively enumerable. Thank you very much.